Not ex- Which of the following Kharash effect will operate? Kharash effect will operate where you have HBr with peroxide. Simple. So we have a double bond with HBr in the presence of any peroxide form. Okay, this kind of peroxide form. So if you have a peroxide group, then first, what are the conditions you see? We should have an unsymmetrical alkene, which means CH3, CH double bond, CH2. So you can see here there is one hydrogen, here there are two hydrogens. So it's unsymmetrical alkene. And then you're supposed to react with HBr, but that should be in the presence of a peroxy group. Now notice here, in this case, no Kharash effect is observed. In this case, no Kharash effect is observed. Now between these two, if you notice here, there is no unsymmetrical alkene because both sides, the number of hydrogens are same. Hence, we will not be able to differentiate that there is a Markovnikov or anti-Markovnikov addition. By the way, Kharash effect means anti-Markovnikov addition. Okay, so only B can show the anti-Markovnikov addition form. Done. Right. See the next question. If you have an alkyne react with this reagent, the reagent is called Lindlar's catalyst. This is called Lindlar's catalyst. Lindlar's catalyst would make an addition to give cis alkene. So here, anyways, we will get A as CH2, CH2. Then you are making a chlorine and water addition. Chlorine plus water would give us HOCl plus HCl. In this HOCl, HO minus and Cl plus are the electrophile and nucleophile that will attach. So on this double bond, you need to make CH2 with one Cl here, CH2 with one OH here, this way. Okay. So you can clearly see that option C is the one which is matching. Got it? Next, see the third one. If alkene is treated with concentrated H2SO4, now see the mechanism, everybody. So if you have an concentrated H plus, first the pi bond will attach, it will generate a carbocation, and then the second mole of pi bond will attack on it, giving an attachment here like this. And as this pi bond attacks on it, you'll get a positive charge here, and that positive charge will undergo carbocation stability and reach to this position. And at this position, it is very stable. And from there, because it is concentrated, it will prefer more elimination over substitution. So you will get a double bond. So it is happening via even mechanism and you will get a double bond form. Now, this is what you will get. And thereafter, H2 by Pt will reduce that into hydrogen and hydrogen. So therefore, B is the more appropriate answer here. Okay. Next, see the fourth one. In which of the following reaction Markovnikov's rule is violated? Okay. Means it will go for anti-Markovnikov addition or a Kharash effect is observed. So you would notice that if you have a lone pair present here, okay, that lone pair can definitely help in conjugation like this. Got it? So when the lone pair helps in conjugation, first thing everybody notice, I am not using peroxide in any of the options here. That is the first thing you need to note. That means is it possible that without using the peroxide, still can we go for anti-Markovnikov addition? That should come to your mind. Now, yes, indeed. Why it is? Check it out. What if you have, let's say, CH double bond CH2, an unsymmetrical alkene, but this time there is a strong withdrawing group, that is electron withdrawing group. electron withdrawing groups like NO2, like CHO, like COOR, like cyanide or CCl3. Any of these groups are present. Very strong withdrawing groups are present. Now, imagine if you're thinking for going an Markovnikov addition, then what will happen? You will expect that the carbocation should form here by Markovnikov addition. But because of its strong electron withdrawing group, this carbocation will be unstable. Instead, what you will do? You will try to keep the carbocation slightly far away from the electron withdrawing group. So you will add here and then get CH2 plus this way. So in such situations also, you will have to forcefully go for anti-Markovnikov addition. Clear? Now come back to the question and see in which case that happens. It is clearly observed that this is donating group, lone pair on sulfur donating group, nitrogen lone pair on nitrogen having a lone pair donating group. Only NO2 is a strongly withdrawing group, which means in this case, forcefully we have to go for anti-Markovnikov addition. Right. Next, 3-phenyl propene on reaction with HBr gives a major product. Okay. So structure wise, if you notice, this is propene and 3-phenyl. That means pH is here. Okay. pH is here. Now again, the same problem, will come here. Check out. If you get given what is a major product here, check. If at all we react this with HBr, correct? HBr, you might have a chance of getting carbocation here, CH3 here, and phenyl group here. The other part is pH here, like this, CH2, and hydrogen getting added here, right? Positive charge coming on this position. So now you might be again confused. Should I go for Markovnikov addition? Should I go for anti-Markovnikov addition? Now think about it. Is phenyl that strong withdrawing group? First of all, phenyl will have very, very mild minus I effect. Because positive charge is here, this phenyl is only going to give you mild minus I effect. But if the carbocation comes here, this methyl will help stabilizing the carbocation. But if the carbocation comes here, this methyl, these two carbons will not be helping sufficiently to make the carbocation stable. So in such case, what do we do? This you will follow for major product. This only you should follow for major product. So in such case, which one do you choose major product? This B. You can see this will be the major product. Okay, right. Let's come to the sixth one. If you have HBr and A is predominant in this case, which means I have to make an Markovnikov addition here. So because the question clearly suggests, the way it looks, you can see the pi bond how it is. It is definitely going to go for Markovnikov. That means the pi bond will take H plus from here. So what do we get here is CH with a plus charge and CH3 following Markovnikov's rule. Because it is secondary, we don't have to worry about, stability wise. Then it will go all the way onto the tertiary position. So the rearrangement goes up to tertiary position. And thereafter the Br minus will attack on this position, thus giving it bromine on this position, giving a bromine on this position. So which is what you would notice in option B. Clear? Right. Seventh, in the following reaction, A plus B, the major product is, so first you will have double bond here, H plus, you will get a positive charge here. Thereafter, methyl shift will happen better because this time all three are methyl groups only. Hence, we will get this way with positive charge here. Once you get a positive charge here, then H2O getting attached onto it. So you will get this as OH on this position. OH on this position. That's it. This is the product that you will get. Tertiary alcohol product. Clear? Any doubts so far in the first seven questions, everybody? If you want to browse any question, you can please do ask me. Otherwise, I'll go ahead. See the options here, which is tertiary, the B part again. Everybody's following? Perfect. Let's go to the eighth one. The correct order of alkene reactivity towards an electrophile is mentioned in. Okay. Towards an electrophile mentioned in which case? Check. First case, if at all I make an carbocation here, right? So let me address the first option A case. Imagine I added a proton here and then I got CH plus and Cl. And on the other hand, I got CH3, CH plus and OCH3. See, oxygen has a lone pair which can strongly support it. And you know that oxygen's plasm is very, very strong, donating nature. While chlorine, although there is a plus I, its minus I effect is huge. So it is in a way deactivating that positive charge or destabilizing that positive charge. So which tells us that this order is not correct. You need to search for more stable carbocation only. Check out in the B part again. Okay, check out in B part. Same logic here also. If at all I get a positive charge here with chlorine following Markovnikov's rule versus carbocation here. Although, again, like I said, chlorine might be donating, but at the same time, it is strongly withdrawing. But in this case, both of them, both the methyls are strongly donating, which means, where is it? Oh, sorry. In this case, there is a problem. I'll tell you why. See, in this case, if you compare, we have a positive charge here. Chlorine is donating by plus N. While here we have a positive charge, this is donating by plus I. It is donating by plus I and hyperconjugation. This side also it is donating by plus I and hyperconjugation. Now guys, please tell me, if I get a positive charge here, the lone pair is pushing electrons that will complete the octet here. See, in the first case, if you notice, both of them are completing the octet. Then you are comparing the effects of it. So problem is not about completion of the octet. This is completing the octet, this is completing the octet, but this is strongly donating as well along with octet completion. That's why this will have very high rate of reaction. But here, if you notice, this reactant is completing the uh, octet completion, but this is not making octet completion in any of the forms. That means if you provide plus I effect, hyperconjugation, this is not going to make a large stability over it. So that means even this one, if you notice, is not going correctly. Ethene and propene. So you see ethene, CH2 double bond CH plus. Sorry, ethene after adding H plus, you will get this as CH3 CH2 plus. Propene this way. This is propene. So between these two, if I feel like, you can see that propane definitely has more stable carbocation. So this one is also wrong. D. If I get a carbocation here with OCH3, definitely it is completing the octet and strongly donating. While here, OH is slightly far away to make any donation. So though there is no resonance directly that can help here, correct? So that means instead it is actually withdrawing slightly. So this is not very stable carbocation, which means this order is perfectly correct. I hope all of you understood this logic in eighth case. Right. Let's notice the ninth case. Cis 2 butene is making an HOBr addition. Okay. Let me remind you once again. If you have a cis molecule and then you are making an HOBr addition, in HOBr it is HO minus and Br plus getting added, and you know that it is going to be an anti-addition. And if you have a cis making an anti-addition, you should get a Fisher projection of threokind. Threokind means like this, with methyl and methyl, with one side OH, the other side bromine. Similarly, the mirror image of it, OH here and bromine here, methyl and methyl. And you'll get 50-50% of both. So overall, you will get racemic mixture here. So check out which one is the correct product. OH and Br been added on the same side. Erythro. Erythro is not correct. OH and Br are added the opposite direction, which is correct. Now, if I put the Fisher projection back here, these two are hydrogens. That is not correct because we have a cis 2 butene. There are only, this methyl is here. That is not going to be a cis form. So that is also incorrect. Here, OH and Br are opposite, but this CH3 is again here. So that is also not correct. Here. So therefore, which one is correct? Only the 3O kind is correct here. Okay. See the 10th one. HBr is been added. Peroxide is been added. So now we need to check out which one is going to be more stable in this case. So check. First one. We have H plus being added here will bring positive charge here, which is following Markovnikov addition. But have you noticed here it is given peroxide, so I can't go there. I have to take the peroxide route, which means this way, like this with a radical, you will notice that H plus will get added onto this position and radical will build up here only. So, sorry, Br will get added here and radical will build up here only. And then it reacts with further HBr to make an addition this way where you have hydrogen and Br getting added. This is the anti-Markovnikov addition. Got it? This is anti-Markovnikov addition. Okay. If you check out the structure, it is like this. This is methyl, this is bromine. Okay. So what is the numbering, everybody? IUPAC wise, if you see bromine alphabetically come first. So 1, 2, 3, 4, 5. So where is it situated? So it is 1 bromo, 2 methyl, cyclopentane. So which one is your answer? So you can see A is the more appropriate answer. Okay. Check out the 11th one. I have a trans molecule making bromine. So addition of bromine is an anti-addition. So we know that trans and anti-addition will always give you erythro. So erythro will be like this with methyl and methyl, with Br and Br on the same side. Listen, if both Br are on the same side, you can easily notice that there is a plane of symmetry existing. So if there is a plane of symmetry existing, this will become a mesoform. Correct? So what we get is a mesoform. So meso 2,3-dibromo butane. So option what you will get is A. Okay. See the 12th one. Out of the given reactivity of the four alkenes for hydrocarbons, a hydrogenation reaction. So hydrogenation reaction mainly depends upon crowding. More the crowding it is, less is the reactivity. Hydrogenation means addition of H2 in the presence of a metal catalyst like nickel, platinum, palladium, and so on. So you need to figure out which one has the least amount of crowding in this case. Got it? So you see, first this one has the least crowding. Then afterwards, this one has the least crowding. Then this one has less crowding, and this one has the highest crowding. Why? Now you might see, sir, between these two, how did we decide? You need to decide on the basis of some symmetry. See, fourth one is still symmetrical because both methyls are distributed. But here two methyls are at the same site. which makes it even more difficult for adsorption on the metal surface. And if these molecules does not go all the way to the metal surface, they cannot be reduced with hydrogen. So this kind of, bulkiness, very high bulkiness on one side is not going to help with hydrogenation. Hence, this B will make more sense. 1, 2, 4, 3. Got it? So in case if you want a reason, I'll write it down. So here it is all about, okay, less hindrance, less hindrance and better symmetry. This is what you need to look into. Next, 15th. The reaction of this with HBr will give you what? Okay, notice this carefully. HBr can go Markovnikov addition, but this is symmetrical given, correct? Here it is symmetrical. So you are wondering whether I should add H here and then Br here, or whether I add H here and Br here, correct? So make a carbocation on both sides and check which one is better. See, if you have it like this, with OH, imagine a carbocation coming on this position. Then we have CH and CH3 with hydrogen added here. Okay, clear. Now notice this one. The lone pair on oxygen is pushing, electrons are pushing, pi electrons are pushing. Correct? This way it is getting highly stable. But on the other hand, if the positive charge is, away from it, like this, I'll remove this part. Check out. If CH2 is here and positive charge is here, then benzene is of no help now. Benzene's resonance is not helping here. So this is a less stable carbocation. So you need to check out in this direction. So in this direction, if Br is been added, the answer would be B. Correct? Br will get added at benzyl position. Okay. Next. Check 14. In the following reaction, ICl, Markovnikov addition is. See, in such cases, I told you, you just need to check out which one has electronegatively more positive and negative. Chlorine is more electronegative, so that will act negative and this will act positive. And you need to follow a Markovnikov addition when you have an unsymmetrical alkene here. So you know that iodine will get added onto this side, chlorine will get added onto this side. So iodine should be at the terminal part, chlorine should be inside. So which is A. Okay. Check out 15th. NOCl is the same logic again, same compound. This will be NO plus and Cl minus. So NO plus should be at the terminal side. Chlorine should be inside here. So again, option A. You can see again, you are getting the same option A. Okay. Again, till 15, any doubt, beta? If anybody has felt like, okay, something I rushed or you have felt like, okay, I need to check again, please let me know. Any doubt? Check 16. The major product of the following reaction is, okay, first, you would have it this way with carbocation forming at this position by Markovnikov addition. And now you can see ring expansion is possible. Ring will expand here. You will get a 5-membered ring like this with OH. If I put the numbering, this is carbon 1, 2, 3, 4, 5. So this is carbon, sorry, this is not CH3. This is not OH, this is CH3. Okay. So this is carbon 1, 2, 3, 4, 5. And on second position, we had positive charge. And that positive charge will migrate. And on fourth carbon, we have OH. Fourth carbon, we have OH like this. Okay. And it will shift onto this positive position here. And OH will be here this way. And once it reaches to this positive position, what do we get? We will get OH and because it is hydrolysis, another OH will be added on. Okay, so which is that product? You can see option C. Any doubt with 16th? Right. See the 17th one. Wherever you see, you know, a pi bond here this way, let's say you could notice that pi bond present here. In such case, first concentrated H2SO4 will make an protonation. See, there are two things which you can do. Either you can add a proton here, get a positive charge here like this, or concentrated H2SO4, will it just simply add on proton getting a carbocation, or will it favor adding a proton with oxygen? Who's better donor here? You know that oxygen's lone pair is a better donor. So you will get a carbocation formation here. I mean, you will get OH2 plus formation first. So you will get this as double bond having a positive charge here. And thereafter, one methyl shift can happen on this side. So if the methyl shift would happen, you will see like this. One methyl got shifted, positive charge has come here. Now see the number one, two, three, four, five, six, six carbon. So pi bond from here will attack on it. So I will get a six-membered ring like this. And here there are two methyl groups. Positive charge will come here. Methyl will be here. And this, if you make an elimination, because concentrated H2SO4 demands elimination, so that will make a double bond here. Right. So this is the kind of double bond you should get. So which is option C. Everybody good with that? Notice 18. Consider the following rearrangement reactions here. So check again. We have like this. First, a positive charge will form here. Thereafter, acha, it's already given. My mistake. We need to check out which of the following coordination represents correctly. Check. First, a positive charge will form. That positive charge will undergo uh, rearrangement by ring expansion. And from rearrangement, after rearrangement, then Br minus has been added. So can I say here there will be one transition state, here there will be one transition state, here there will be one transition state. So there are three transition state and two intermediates, two intermediates. And remember, addition is always exothermic. Elimination is endothermic, addition is exothermic, which means your graph should be something like this. So if you start from here, so first you should become a first carbocation. From there you should become second carbocation. Okay. From there, you should become product like this. This is the kind of form you should have, where you have three transition states and one, two intermediates. These two are intermediates. Search for the graph like this, and it should be this line should be product line should be lower than the reactant line because it is exothermic. Which one serve the purpose more, better in this case? In the given options, which one looks more appropriate there? All right. See, honestly, none of them is absolutely given correctly here, correct? So, but the better graph is this one, which I gave you. Okay. Now, is there anything which is closer by here? See, check out. From here, this is adding up here. But when the rearrangement happens, the energy cannot go below this. That is wrong given. At least here, that part is given okay. So it should go like this, then like this, and then, but this should come down. This part was not given down, so just I'll change this graph part. This was supposed to be correctly given like this, one, two, and then three like this. This should have been the correct graph. Okay. C19. Which of the following when undergoes HBr will only form a pair of diastereomers? Check out. If you make a first addition of HBr here, so first one by one we will go. In the option A case, first you know that carbocation will form here. That carbocation will further get rearranged. And after rearrangement, you'll get bromine on that position. So we'll get Br here. There is no chiral center. So the concept of, getting diastereomers is not observed in this position. Second, here you can see chlorine is this way. H is getting added here, positive charge coming here, and thereafter chlorine is here and bromine is coming here. Correct? Now you see bromine is not on a chiral center. So even here, this is not valid because chlorine has a fixed configuration, that is the fixed configuration. So these two are, I mean, if you compare products, there is only one product you will get. Next, check out C part here. C part we have 1, 2, 3, 4, 5, 6 like this. And then OH is this way, correct? And in case if at all I have to add, pi bond onto this, clear? So first H plus you have added here, positive charge will come on this position. And from that positive charge, then bromine will be added onto that. Bromine will be added onto that position. So as the bromine gets added here on this position here, so you will have this chiral center. Now, because it is a chiral center and this is a fixed form, the products you will get is if one is R configured and another one is S configured, the one more isomer will be R and R. So what are these two? These two are pair of diastereomers. Got it? Now here there is no chiral center only. So if at all I do not have that fixed chiral center, I cannot get diastereomers. Here you will get only enantiomers. What is the product? Let me tell you. Like this, we have two methyl groups. First H plus will get added, then Br will come here. So this is a chiral center. So you'll only get enantiomers. Okay. In the first case, you have got only one product. Second case, you got only one product. Third case, you have got pair of diastereomers. And fourth case, you got enantiomers. Please do check. If any doubt is there, you can ask. Right. Notice 20th. The number of intermediates and transition state made during the major product in the following reaction. Okay. I'll do it and show you. Okay. Because in the upcoming problems, you will, when I ask you to solve, there you will always get these kind of questions. So learn and understand how you have to solve these kind of questions. So first we have a double bond here. So H will get added, positive charge will come. The bond will break, it will undergo ring expansion, 5-membered will become 6-membered ring like this, and positive charge is here. Okay, and then after that methyl group is here. Again, you will see positive charge will get migrated onto this position because that is more stable position. And once you get there, you will get the product as OH here and methyl here. Okay. Of course, there will be two products here if you notice. So one will be methyl and methyl on same direction with OH inside, or the other will be methyl and this methyl or opposite direction, but OH, sorry, OH is inside like this. These are the two forms you can get. Clear? Now, if I go across, first from here to here, this is first transition state. So from here to here, TS1, and this is intermediate one. Again, here it is TS2, intermediate 2. Got it? This is intermediate 2. So from here to here, this is TS3 and intermediate 4. Okay, and here intermediate 5. Okay, so this is product, sorry, this is final product. So this is transition state 4. Okay, so TS1, TS2, TS2, TS3, and then I'll write the last one also. So as the OH minus attaches here, so you will get this product. Okay. So how many intermediates we had? Sorry, this is three. Okay. So there are three intermediates and four transition states. So notice it. You can see how many intermediates: TS2, TS1, TS3, TS4. Four of them. And intermediates one, two, three. Three intermediates. So therefore, which one is that? B. B part. Okay. So I hope all of you understood this point. Right. See the next one. Okay, two questions are missing here. Leave that part. Directly come to 23 now. Which of the following are the formed products during this? This we just did it. I'll redo that again. Check. This way we have double bond here. After adding H plus, carbocation will come at this position. Then methyl will come here. Positive charge will come here. Thereafter, bromine will come here. This is the way. Okay. This is the product formation which you have. So option A is correct. Now notice he is not asking about one product, is or, which means write all the minor ones also. So minor ones, what are the products you can get? First, I can get Br here directly when the first carbocation is forming, isn't it? Right? Sorry, not this Br. Like this, one Br formation here. And then the second Br will be here. So these two are the products you can get. So which means D is also a product which you can get. So A and D are the possible products in this case. Okay. Now another important factor. ध्यान से देखो. H2O, HBr, then followed by water. Very important one. Followed by water. When water is followed now, water is always in a large quantity. That itself can act like a nucleophile. So that means whichever position bromine you are getting, whatever the products you are getting as bromine, in this case you can see one bromine was here. In the second case, bromine is here. Same positions you replace that with water, which means you can get OH. Okay, now you will get this as OH here and OH here. These two are the other products as well. So now notice this is that product given, even this is the product given. So which means all four are correct products. Now guys, if I ask you, if the question asks, I mean this was also asked in JEE mains, the same question, which of these following are major? See, major will always be the hydrolyzed part. So in that case, this B will become the major product. This is the major product. More than bromine, it is the water's quantity which will be large. So B will be the major product. Everyone clear? Next, check out which of the following statement is correct. First propagation step in addition of HCl in the presence of peroxide is exothermic. So we need to check out what is happening in this first reaction. See, the first propagation step is like this. You have x dot, sorry, first propagation step is this one. HO dot, because it is coming from peroxide, or RO dot, you can take anything. That when you treat with, you know, double bonded carbon here, isn't it? In the presence of peroxide, first it will take away H plus. It will take away H plus from any of this part. 1 second. Peroxide is exothermic. No, sorry. My mistake. See this one. Let me write down from the start. Suppose if you have HBr, reacted with peroxide H2O2 in the presence of heat. So first we will generate the Br dot here. Okay, because peroxide will convert into HO dot. That will take H2O plus Br dot. That will convert into H2O and Br dot. Okay, clear? So you can see this is the first propagation step. So if I have to write the complete steps one by one, please let me write all the steps here. So first step is let's say HX plus, you know, sorry, first is peroxide. H2O2 in the presence of light is becoming 2HO dot. So this is called initiation step. Initiation step. Initiation. Second one, HO dot which is present, HO dot which is present, that will react with HBr and it will convert into H2O plus Br dot. Now you can see one radical is generating the second radical. This is called first propagation. First propagation. Second, if you have this as Br dot and then you add onto a pi bond here, then it will add here and make a dot here. So this is the second propagation. Second propagation. And once the second propagation is done, then the termination will take place. I mean, the third will take place, which is Br plus HBr. It will take H plus H dot, and this is the product form with Br minus. This is how the third propagation steps will be. So let's go back to the statements here. First propagation step in addition of HCl in the presence of peroxide is exothermic. So we are talking about the first one here. So see here, if it is HCl and it is becoming Cl dot and forming H2O, it is been said that it is exothermic, which is correct. In the case of HCl, there is no problem. This bond will break. H2O is made. H2O is a very, very strong bond compared to that of HCl. So definitely it will make an exothermic change. So first one is correct. Second statement. First propagation step in addition of HBr in the presence of bromine. Bromine is also exothermic. That is also correct. It is only iodine. It is only the iodide form which is endothermic. Otherwise, all of them are exothermic. Second propagation step in addition of HCl in presence of peroxide is exothermic. Second propagation step is this one, where Br dot is getting added to get this one. The problem what happens when you have Cl dot getting added, this wasn't observed to be exothermic, it is slightly endothermic observed. And because it is endothermic, we say that HCl does not make a Markovnikov of addition. So which means this, you know, C, if you notice, is incorrect because it is said it is exothermic. So that means here this C is incorrect. Second propagation in HBr is exothermic and precisely correct because it is exothermic only we say bromine is more selective and it can make a better reaction than chlorine. So anti-Markovnikov is only observed in HBr and not in HCl. Okay, clear everyone? So please tell me any doubt up to this part again. These are the next 7 questions which we discussed. Which of the following give enantiomeric pair during addition of H2? This has been a JE question and very frequently asked. Very simple though, but always chance of making mistakes. Notice here we have a chiral center here. Correct? There is a sorry, not chiral center. I mean there is a double bond here. Now suppose if H2 is being added here. So we can see H and H being added here. Will there be any chiral center happening here? Okay, you need to check that. So like this, we will have, like this, we will have, and then we will have like this. Okay, now this is ethyl, methyl, and this is ethyl. So you can see this is also a chiral center, this is also a chiral center. Okay, so it would form two chiral centers in this case. Clear? Because it is forming two chiral centers and the addition of hydrogen and hydrogen happens simultaneously. That means it is a syn addition here. So we can never say you will get enantiomers. We can never claim that we can get enantiomers because two sides, if it gets added from this end, two sets if it is getting added from this end, those two not necessarily have to be enantiomers. Okay. Second one, if hydrogen and hydrogen gets added here, so what do I get? So like this, like this. This is ethyl, ethyl, methyl, and methyl. Okay. Now, could you recall something, everybody? What is this form? This form is a trans form. And in a trans form, if you are making an H2 addition, which is a syn addition, so trans, syn, and trio, we should get trio. So yes, which means I will have like this: ethyl, ethyl, methyl, methyl, and hydrogen, hydrogen. And the addition can happen from other side also. That means hydrogen, hydrogen can be here, methyl, methyl can be here, and then ethyl, ethyl can be here. Got it? So if you notice these two are enantiomers of each other. These two are enantiomers of each other, which is correct. So B is correct in this case. Next one. This time you have a cis form here. Check out properly. This is a cis form. But notice this also carefully, that we have a phenyl here. Sorry, we have a propyl here and an ethyl here, and methyl here and methyl here. And you know that if you make a syn addition, so basically I'm talking about C, S, and E. If you have a cis making a syn addition, you will get erythro, which means the hydrogen which what you are adding here will be on this side. Which means if I take the mirror image like this, ethyl, ethyl, methyl, and methyl, and hydrogen and hydrogen. Now you notice that there is no plane of symmetry in this case. Because there is no plane of symmetry, I can say these two are enantiomers. So C is also correct. These two become enantiomers. Last one. Again, I have a transform here. You can see there is a transform. So if there is a transform, you will get a same product here, just like this one. Just like this one. Only one thing I have to change here is instead of, uh, sorry, yeah, that's it. We have ethyl and propyl here. So therefore, instead of this, we will have, you know, this will be propyl and propyl. That's it. That is the only change we have. So B is also correct. So what did we notice? B, C, D. These three are correct. Next, 26. Which is or are incorrect among the following statements? Addition of HCl to unsymmetrical alkene always follow Markovnikov addition, which is true. Okay, right? Sorry, always is said. Sorry. My mistake. Always is incorrect because I told you a case as well like this. If you have, let's say, here we have strong, here we have hydrogen, methyl, correct, double bond, but on the other hand, we have NO2. Okay, this way. Okay, or let me say these two are hydrogens here and NO2 is there. Now, if you react with HCl, although there is no peroxide, it should go for Markovnikov, but the Markovnikov will make it less stable because positive charge will come here. As per Markovnikov, positive charge is supposed to come here, but that will be less stable because NO2 is strongly withdrawing, and which which tells us that fact that always is not, the correct words to choose. Addition of chlorine water to propane forms diastereomeric pairs only. Okay, diastereomeric pairs only. So check out what do we get. Got it. So here, so we need to figure out incorrect ones. So first one is incorrect. Second one, chlorine water dash turmeric. It will not give dash turmeric, it will give enantiomeric because you will have chlorine, bromine here, chlorine and OH here. And if I take the mirror image, I'll get this as chlorine and OH here. So that definitely make it as a enantiomeric form. Next, addition of Br2 with CCl4 to cyclobutane forms both cis and trans isomers. Okay, cyclobutane. See, if you have cyclobutane here like this, cyclobutane. You will have Br here and another Br like this. Or you can have like this, one Br here and one Br here like this. So now if you notice these two are not, there is no plane of symmetry between them. So they become actually enantiomers. These two are enantiomers of each other. Correct? So it said it forms cis and trans isomers. And these enantiomers, everybody, bromine and bromine are always opposite in both enantiomers, which means it is always going to be trans. So this is also incorrect. C is also incorrect. B is also incorrect. D. Major product 4-methyl 1-pentene and HBr is 2-bromo 2-methyl pentane. 2-methyl 2-bromo pentane. Let me put that here. What is that question trying to say? 4-methyl 1-pentene. So I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4-methyl here and 1-pentene here. We are reacting that with HBr in CH2Cl2. Okay, in non-polar solvent. So methyl will be here, correct? And by Marconic of addition, bromine will come here. Got it? By Marconic of addition, bromine will come at this location. So now question asked is, the product is 2-bromo 2-methyl pentane. So how come 2-methyl? This is at which position now? 1, 2, 3, 4, 5. So it should be 4-methyl, right? It should have been 4-methyl. That is not given correctly. So even D is also incorrect. So all A, B, C, D are incorrect in this case. All okay? I got 27. Which of the following represents correctly the product of the reaction between Z2-butene with bromine and CCl4? Okay. What is Z2-butene? See, if you have 2-butene like this with H here and H here, this is methyl and methyl. As per CIP rules, this is rank 1 and this is rank 2. Here also it is rank 1 and rank 2. Now, if the high priority group, rank as in priority, these two are high priority groups. If two high priority groups are on the same side, that is called Z isomer. If the high priority groups are on the opposite side, that is called E isomer. Okay. So what we are talking is about a Z isomer here. And Z isomer in this case is cis. And bromine addition is an anti. So cis plus anti should give you 3O. So which means how should be the product here? So this way, and it should be Br and Br on the opposite side, methyl and H should be on this side. This is the Fisher projection. If you check out the Fisher projection and put it back into the Newman projection, so how does it look like? We will have this as methyl, and methyl here with Br and Br on the same side. This is how we expect. Yeah. Now you have to make sure that all these four diagrams are they matching with this Fisher projection or not. That's the part you need to check. So let's see how we can do that. Let me add one page to this. Notice in the first case, beta. First case, what you do, everybody, this will be a good revision for your identification of conformations and all the projections. So please learn this carefully. Suppose if you have a bromine here like this and another bromine here like this. In case if you want to make a Fisher projection for this, you need to first change this into uh, eclipsed form and not in a staggered form. What does this mean? If at all you are watching this molecule from the side, it appears like this. with bromine is here. Okay, bromine is here, correct? Hydrogen is here, got it? And another, in this case, hydrogen will be, sorry, we rewrite that this way. We have on back side, we have like this. So check it out. Bromine is here, bromine is here, methyl is here, methyl is here, and these two are hydrogens which were not observed. This is the sawhorse projection. This is sawhorse projection. But this sawhorse projection, I have to rotate the carbons, center carbon, so that all three will be on the similar side, which means I have to rotate it like this. Bromine will should come here, hydrogen should come here, methyl should come here. As you rotate, now we notice Br is here, methyl is here, H is here, H is here, Br is here, and methyl here. Correct? This is how it is. And now, if you watch the molecule from here, what you can do, you can take this molecule, correct? Check it out. You can paste it here and then rotate it like this. Rotate it this way. So, which means on rotation, you will notice that this line and bromine, this is how the line would be. So, which means as you stand from here and start watching here like this, so this line will be observed. Okay, a line will be observed where bromine are up, and then methyl is coming out of the plane. So methyl will be on the right, and H will be on the left. This is how it appears. Okay, and this is Fisher projection. You can make a Newman projection also. You can make this as a front carbon, this as a back carbon. Front carbon has, you know, this way hydrogen, methyl, and bromine. And backside we have like this, where bromine is at the same position we have bromine, methyl at the same position we have methyl, hydrogen where we have same hydrogen is present. So this is the Newman projection. So I guess for the first case it is clear. Okay. Second case, it is very similar. Second case, this is already given in eclipse. You don't have to change anything because it is already given in eclipse. So what you can do, you can check out this way. First, write the uh, projection, Sawhorse projection. The Sawhorse projection goes like this, and in that, bromine, methyl, and methyl are already at the same location. So methyl and methyl, hydrogen and hydrogen, and bromine and bromine are already at the same location. Okay, so which means it is same as the first one, correct? It is same as the first one. So A and B are exactly same. Next, check out the third one, correct? Where you need to always check out this, line which is present on the plane. So on option C here, now for option C here, see what we can do. This is the way the line is. Br and Br is, and methyl, sorry, it's coming out of the plane here, and here methyl is also coming out of the plane here. In that case, again you rotate it so that methyls will be on the same side. So this methyl and methyl, if at all I'm trying to bring it to the same side, got it? Which means they won't be coming to the same side, because when you operate here like this, so we will get Br and Br on the same side. But now when it comes to methyls, you will see this methyl is fixed. But as you rotate this methyl, it will go inside. So this methyl and methyl will be like this. So therefore, what do we get? We'll get like this. We will get Br and Br, and one methyl is here, one methyl is here. H and H will be the product formation. This is for option C. Okay. Option D, if you rotate it, in case if you rotate it, again, it will be same as that of this one. Okay, A. So A, B, D are the same kind of molecules, but different forms of representation. Please go through it. Any doubt, you can ask me now. See the next one. Which statement is or are correct regarding acid catalyzed addition of water to cis-2-butene and trans-2-butene? Okay. So notice cis-2-butene. Uh, See, catalytic hydrogenation here, right? Basically, if you have a cis here, then catalytic hydrogenation, acid catalyzed hydrogenation means H plus you are adding, then you are getting water on it. So because you get a carbocation here, H will get added and carbocation getting added here. So you will always end up getting, OH, which a chiral center, which is racemic because you can have both dextro and levo. So whether you start with cis or whether you start with trans, the product is the same. So therefore, we can say both will form same products, right? Second, they give different products. No, both the reactions are regioselective, which is correct because out of the region here, I mean, I could make OH on this position or I can make OH on this position, but we are choosing at the second position. Therefore, this is regioselective, and products in both of them are optically active. Okay, products in both reaction either are optically active. No. See, notice products in both reactions either are optically active. First of all, both the products individually are optically active, but as a solution, it is racemic mixture. Will it be optically active? No, it is not optically active. So such statements do not take it as optically active. The statement does not say individually look into the products. No, because we cannot isolate them. So if you have the product form, that solution is optically inactive. So therefore, this statement is wrong. So what are the correct answers? Only A and C. All good? Now, come to this integer type. How many of the following gives one chloromethyl cyclohexane as major product? Okay. I want you guys to try for a minute, then I'll explain. 2, 4, 1. Okay, everybody got different answers. So, hmm, check. First case, if you notice, you will get H plus getting added here, positive charge will come here. So uh, it is already at the stable position. So there only chlorine will come. Okay, here. So second, B1. Here we will get carbocation at this position, and then ring expansion will happen. Carbocation will come at this position, and that will give you a positive charge here, and finally chlorine will, sorry, I'll write that also. Then carbocation rearrangement will take place, and finally chlorine will come at this position. Okay, so here also you will see only here this product is correct. B is correct. Clear. Next, C. In the case of C, you can notice that first carbocation is made here this time. Why here? Correct. Because if you
Yes,
get a
sir.
positive charge here, huh?
Sir, I'm not.
Huh. I'll explain about the first one again. Okay. Sorry. First, let me explain the third one, then I'll come to the first one. Okay. First, see, you have a direct double bond form here. You can get a positive charge here, positive charge here. This is tertiary, this is secondary, but yet you will go for secondary position. Reason is very simple. If you get at this tertiary position, it will have more strain. So you'll break this, make an expansion. You get a positive charge here, and that will get rearranged. You get positive charge here, and from there you will get a chlorine on this position. Okay. Next, you can see HCl here. It is already simple. Here you will have CH3, and here you will have CH. That's simple one. Here also it is simple one. Here like this and Cl. And here first H plus will get added here. Positive charge here. It can get rearranged. So positive charge will come here and chlorine will come at this position. Chlorine will come at this position. Okay, got it. Now question is about, I mean, the slightly debatable form is only about A and C. Will should we go A getting a carbocation outward here or inward here? Outside, you don't see much of a stability here on this carbon because it will be primary carbocation. So primary carbocation is not very stable. But unlike that, in C, you have a secondary carbocation. So should we go with this or no? That is a second question. I mean, that is the second thing that should come to your mind. Now, notice here. Now, here is an interesting part, everybody. If you have a five-membered ring, for five-membered ring, you should only go for outward if outside is at least tertiary or more stable than this position, more stable than this position, which means, let me show you an example. If you have like this, you have double bond this way. In that case, definitely you should go, make a carbocation here and then follow up with ring expansion. But if you have, you know, only double bond like this, correct? Uh, Double bond this way. In this case, the first case here, and if you have a double bond like this, in both these cases, you will make carbocation on the five-membered ring only, like this. This one positive, and here also you'll make this one as positive here, correct? So in the case of tertiary only you do it. For primary and secondary, usually it will not go for it because five-membered ring is not highly strained as that of four-membered. But in case of three-membered, four-membered, even if you have a primary position, secondary position, or tertiary position, in all cases you will try to make a ring expansion. Okay, here,
So,
out.
so in the question we are asked one chloromethyl.
Sorry,
So,
it is one chloro, one methyl. Sorry.
uh,
Oh, that was a confusion. Sorry.
yes, sir.
One chloro, one methyl. Hmm?
Thank you, sir.
Hmm. Samyak, yes, beta.
Sir, how is the cation shifting in B and C?
Why cation shifting?
Yes, sir, like there's a cationic shift in.
See, uh, notice the braking beta. Braking started happening here. From this position, you started pushing electrons here. So now you have one, two, three, four, five, six. So this is that six carbon. But positive charge come at this position, which is this one. And this is at secondary position. So hydride shift can happen. And again, you can get even more stable, which is tertiary position.
Okay, sir.
Okay.
Yes, sir.
I hope all of you got that. Right. Likewise, try the second one. Okay. Check if you're able to get this or not. I'll explain in a minute's time. Right. So in this question, you can notice bromine addition on a cis form here. You know that this is an anti-addition, and cis plus anti-addition will give you 3O. So first write down that two carbons only. Then you can fill the rest of them later. So one Br will be here, one Br will be here, H will be here, H will be here. And then you write the top bromine here, CH3, H here. And then you write the bottom one, which has bromine here, H here, and CH3. Correct? And similar group, you can get it on the other side also. That means this same thing. I need to, sorry, I need to just change it based on the structure here. So I think you get, you do understand how to get that. Next one. Here you do the same thing. First, we have this way. We have BR here and BR here. And above, we have another chiral center with BR here, CH3 here, H here, correct? And H here, and CH3 here, correct? Now notice this can be written in the other way around also. That is this way. I can write CH3. This BR is fixed, but the second BR and the third BR I can rotate it. I just need to put 3O. So these two are the 3O forms. Okay. In the case of reaction 2, if it is trans, I should put them into erythro form. So I should have BR here, H here, and one BR here, and CH3 here, CH3 here. The other form which I can write here is these two BRs could be on the left hand side. So I have BR here, BR here, BR here, H, and then we have methyl and methyl here. These two are the forms for Q. Next here you can have first I'll write down these two where we have CH3 here. Then trans plus anti will give you BR and BR here. So H here, and one more BR here. So H here and CH3 here. And then we will have these three here. So we'll have BR here, H here, CH3 here, and then BR here, H here, and CH3 here. Done. Right. Okay. Right. So let's come back to this one. Check. In the first case, whether you keep BR on the left and then BR on the right, both of them will be optically active only. Both of them will be optically active. And they'll be two different products. So I can write two different products here. Here, if you notice, uh, this product and this product look exactly same. Okay. Sorry, are they same? No, they are not same. These two are two different mesos. Okay, they are both meso. This one is meso, this one is meso, but they are not exactly same products. Correct. So I'll have two different products here. Ah, next, check out this one. In this case, here we have again meso and mesoform, but these two are also different mesos. So you will get two mesoforms here. And lastly, here there are one meso and one normal case. So again, you will get two here. Correct. So we are actually getting all different compounds only, right? So it's not like we are getting same compound, but some of them are meso, some of them are not. So answer is 8. Now the question would have been much appropriate if the question was asked how many meso compounds were formed. So let me write down that here. Okay. So number of meso products. Meso products. So how many meso products? Check it out carefully. In the first case, you will not get any meso. Second case, this is meso, this is meso. Both of them are meso. Sorry. This one is not meso. Here, this one is meso. So this is meso. And next here, if you notice, here this is meso and this is meso. So we got two meso and one meso here. Total three. One plus two here, and then last one. Last one you can see this one is meso, this one is not. So again, I'll get one more meso. So total there are four mesoforms you can get. I guess this case is clear, everybody.